Okay, so let's work through some examples with using matrix decomposition. So I'm going to use the Swiss data set, and I'm going to define my y as fertility, and I'm going to define my x as everything in this matrix except the fertility. So just let's look at head of x, and you can see it has agriculture, examination, education, Catholic, and infant mortality. Let me just, for convenience, define n as the number of row of x. So probably the easiest way to get at these things is to do so-called principal components. There's a princomp function in R. So here's the princomp function. I'm putting core equals true here, and the reason is because I'm not so sure about the units of these measurements, and so I want them to be comparable. So if we do a decomposition on the correlation matrix, that's a little bit more comparable across variables than a raw decomposition. So for example, if I were to plot the cumulative eigenvalues versus the cumulative sum of the eigenvalues versus their overall sum, that's the percentage of variation explained by that component. So one principal component explains just under 60% of the variation in the data. Two principal components, so that's including the first and the second principal component, explains over 70% of the variation. Three principal components almost explains 90% of the variation. Four explains close to 100%, and then five explains 100% because five at that point is just a reorganization of the matrix X. So let me just show you. So remember that the principal components is the decomposition of the correlation matrix. In this case, it's either the correlation matrix or the covariance matrix. In this case, again, we did the correlation matrix just to get rid of the units of the variables. So we could do it directly by taking by taking eigen of the correlation matrix. So core of x here just calculates the correlation matrix of x, so a 5 by 5 matrix in this case. And eigen just calculates the eigenvalue decomposition of that. So if I look at, for example, names decomp2, it gives me my values and my vectors. So for example, if I were to do diag of decomp2, let's see, the transpose of this vectors times decomp2. So if I take the v transpose v, that should just give me a vector of ones. Okay, so that's just saying that v transpose v, the diagonal of that is ones. We know that all the off diagonals are zeros. That's just reminding us that v transpose v, that v is an orthonormal basis for R5 in this case. So another way to do exactly the same thing is through the singular value decomposition. First, we need to normalize our columns. So here I just go over the columns and replace them with their normalized values, subtract it off the mean and divide it by the standard deviation, and then I directly take the singular value decomposition. Now decomp3 is the singular, decomp was the principal component decomposition, decomp2 was the eigenvalue decomposition of the correlation matrix, and decomp3 was the singular value decomposition of the normalized X matrix. So decomp3, let me show you the names of the variables it returns. So decomp3 gives me three variables: d, the singular values; u, the left singular vectors; v, the right singular vectors. So just to show you that these are all getting at the same thing, let me combine the eigenvectors from the eigenvalue decomposition of the correlation matrix, and I'll do it with what are called the loadings from the princomp function, and then I'll also grab what is the V matrix from the singular value decomposition. And here are those three quantities. Notice, like, take for example this first column, comp1, comp2, comp3, comp4, 0.524, 0.258, and so on. Okay, then if I go down to the output from print comp, 0.524, 0.258, negative 0.003. There's no reason, by the way, that the signs should have to agree in this case. I think we were just fortunate that we did because they're using underlying the same exact numerical libraries. But there's no reason that there's a sign invariance to all these decompositions. And then, of course, the singular value decomposition gives us the same things. And then if we go through the second row, it's the same thing again. Okay, so what we see is that the three different approaches are giving us the same V matrix. And then if I were to plot my eigenvalues, okay, here's the first row are the eigenvalues from the eigenvalue decomposition of the correlation matrix. The second one are the eigenvalues from the print comp function that calls those standard deviations, so we have to square them to get the eigenvalues. And then the third one are the squared singular vectors. Now, I had to divide by n minus 1 because remember there was this idea that when I wrote the formulas up on the board, I was omitting that 1 over n minus 1. Now let's look at the scores. So I'm going to take the singular value decomposition scores and plot them versus the scores from the print comp function. And if you look, of course, they perfectly agree. Now notice the scale is off here. And again, that's that n minus 1 factor that when we take the correlation, it's divided by n minus 1. Whereas when we just take x transpose x, we have not divided by n minus 1. So it's off by, that's what's representing this change in scale. The other thing is we could manually calculate the U matrix from the eigenvalue decomposition of the correlation matrix. So we need to take the normalized x vector, multiply it times the eigenvectors from that decomposition, and then multiply it times 1 over the square root of the eigenvalues. And there again we see that they just agree if you look at the plot. Now let's show you how you might use these things. Let's just take the singular vectors from the singular value decomposition, and I'm going to just take, let's say, the first 4 of them. So I've omitted one variable, okay, and I'm going to try doing a linear model with my y, with my u as my set of predictors, and look at the r squared, okay, it's about 70%, and then I'm going to compare that to the linear model using all the x's, which in this case gives me about 70% as well. So by virtue of removing that extra variable, we have eliminated, we have basically found the linear combination of our regressors that retains the most amount of variability in our x's, and so we can remove a regressor and still have just about the same amount of variation explained in our y. And then the last thing I want to show you is, so if I were to do summary lm y tilde u, okay, we see these estimates 70, 57, 26, negative 16, 24. Because u is orthonormal, I can just do t of u star y, and that should give me the same things, 57, 26, negative 16, 24. In this case, the intercept is taken care of in u because it's orthogonal to the intercepts. We'd centered the x before we had done anything. So at any rate, that's how we start using principal component decompositions. And more than anything, I know this is probably a little bit far along relative to where the class should be at this point. More than anything, what I'd like to have, for people to have gotten out of these series of lectures, is how convenient things kind of work out when we have orthonormal bases in linear regression, and how nice the calculations are. And then second, in specific, I hope you might, a little bit of the language of singular value decompositions and principal component decompositions will have rubbed off in you, and also to show you via the computing that none of this stuff is magical. The print comp function is just a collection of singular and eigenvalue decompositions that we could do manually, and the print comp function just makes it a little bit easier. Okay, so we're looking forward to seeing you in the next class.